Welcome to today's Explainer. We're diving straight into a multi-billion-dollar engineering dilemma. When building a brand new high-speed rail network, do you adopt the proven global standard, or do you adapt to your country's massive pre-existing infrastructure? We're going to look closely at the fascinating world of track geometry and explore a massive infrastructure decision that changes the very foundation of how trains operate.
Here's the agenda for today's Explainer. 1. The foundation, track gauge. 2. The global standard, 1435 millimeters. 3. India's broad gauge reality. 4. The interoperability argument. And 5. Defying the global paradigm. Let's jump in.
Section 1. The foundation, track gauge.
Okay, so before we can even think about sleek bullet trains or massive concrete viaducts, we literally have to start from the ground up. Track gauge. Basically, it's the exact standard distance between the inside edges of the two parallel rails. And this isn't just some arbitrary number. If your wheels don't match this exact measurement, well, your train isn't going anywhere. It's a hard, physical commitment that locks in a country's rail infrastructure for generations.
Now take a look at this formula. You'll see that gauge, represented by that G right there, isn't just a simple tape measure distance. It's actually a foundational mathematical variable used by civil engineers to calculate track cant. Cant is essentially the super elevation, or the banking, needed to safely guide trains around high-speed curves. Think of it like a sharply banked racetrack. Because G sits right up there in the numerator, changing the gauge mathematically alters the required super elevation, and that directly impacts how you balance slow, incredibly heavy freight trains and ultra-fast passenger trains on the exact same tracks. It's a real balancing act.
Moving on to Section 2, the global standard, 1435 millimeters.
1435 millimeters. That magic number is known as standard gauge. It is the absolute, undisputed heavyweight champion of the railway world, adopted by literally every pioneer of high-speed rail systems globally. If you go out and buy an off-the-shelf high-speed train today from almost any major manufacturer, it is custom-built to sit perfectly on a track that is exactly 1435 millimeters wide. Historically speaking, the intense physics of high-speed curves forced early innovators to make a completely clean break from their past. The strict limits on cant, basically how far a train can safely lean without tipping over or making everyone on board totally carsick, meant countries like Japan actually had to abandon their older 1064mm lines. When they developed the Shinkansen, they laid entirely new 1435mm lines dedicated exclusively to high-speed travel. France did the exact same thing, laying a brand new line between Paris and Lyon for their TGV. You see, you just cannot run a 300km/h passenger train and a slow, lumbering freight train on the same heavily banked curve without completely compromising safety or comfort. So they built separate, dedicated tracks using that 1435mm standard.
Section 3. India's broad gauge reality.
But what happens when a rapidly growing nation decides to completely challenge that global precedent? Well, India presents a truly fascinating engineering case study here. Their massive conventional railway network doesn't actually use the global standard. Instead, it relies on broad gauge, sitting at roughly 1673 to 1676 millimeters. It's significantly wider, and it spans one of the most extensive and heavily utilized railway systems on the entire planet.
So the real tension here lies between these two measurements. On one hand, you have the 1435mm standard gauge. It's globally proven for high speed, sure, but building it means creating an isolated, completely separate infrastructure silo. On the other hand, you have India's wider 1673mm broad gauge. Now, it's not the global norm for high speed, but using it offers incredibly deep compatibility with the country's vast existing domestic lines.
And Indian railway experts took a very firm, localized stance on this. Just look at this 2015 text from the Indian Railways Institute of Civil Engineering. They heavily emphasize a unigauge policy. The main goal? To absolutely avoid fragmenting the nation's railway infrastructure. You know, they had already spent years and a lot of money converting various narrow gauges across the country to a uniform broad gauge just to streamline operations. The last thing they wanted to do was introduce a brand new, incompatible gauge into the mix, even for the sake of high speed.
Which brings us to Section 4, the interoperability argument.
So, why go against a proven global standard? Well, the RITES feasibility report for the Mumbai-Ahmedabad corridor spells out the logic perfectly. By building the high-speed line on broad gauge, the new ultra-fast corridor can physically interconnect with existing Western Railway main lines at key strategic stations, like Vadodara and Surt. This routing strategy means conventional express trains, like the famous Rajdhani and Shatabdi, can literally roll their wheels right onto the brand-new high-speed tracks.
This creates what engineers call ultimate interoperability. Think about it. If there's massive congestion on the main line, standard express passenger trains can just seamlessly divert onto the pristine high-speed infrastructure to bypass the traffic jam. Or a high-speed train could travel the dedicated ultra-fast corridor for the bulk of its journey and then smoothly transition onto conventional tracks to reach a final destination much further inland. This kind of interchangeability absolutely maximizes the daily utility of what is a multi-billion-dollar infrastructure investment.
Finally, Section 5, Defying the Global Paradigm.
Ultimately, this decision boils down to a massive infrastructure compromise. Adopting the 1435mm global standard means you can buy proven, ready-to-go trains straight from the factory floors of international manufacturers, but it permanently isolates your new high-speed network from the rest of your country's rail system. Alternatively, adopting the 1673mm local utility gauge achieves incredible, fluid domestic network integration. But it requires you to design and develop completely bespoke, custom high-speed rolling stock that fits those wider tracks from scratch.
As we wrap up this explainer, I want to leave you with this. When you are building a system designed to last a century, does the daily benefit of local interoperability really outweigh the massive developmental costs of defying a proven global standard? It's a fascinating puzzle, and it proves that off-the-shelf solutions aren't always the best fit for local realities. Thanks